Let us start off with question number 10. The first question is, state Kirchhoff's first law, also known as Kirchhoff's current law. So this one reads, just going to write the description and just write the expression, and you can convert that into description. Sum of currents entering the junction equal to sum of currents going out of the junction. Just write this thing in description and you'll be awarded 2 marks for this one. So let's move on to the next one. Here we have the circuit shown. Okay, we are provided with the circuit. The current in R3 is 0.30 amperes, as we can see over here also. The potential difference PD across R4 is 2.4, which is once again given over here. We can see that as well. Show that R is equal to 4 ohms. So we need to find the resistance of any of the resistor. And that would be same because we know this thing, each of resistor R. So all of them have the same resistance. All of them. So what we can say, the resistance of this one is R, the resistance of this one is R, the resistance of this one is R, and likewise the resistance of this one is also R. So let's try to trace the currents. If all of these resistances are same, and I'm especially concerned with these two resistors. So if these two resistors are same, can we find the current through R2? Would be 0.30, because if the resistors are same, then the current should also be same. So this one is also 0.30. So both the resistors are drawing the same current. They are connected in parallel, but since they have equal resistance, so the current would be divided equally. But then the next question is, can we find the current that is passing through the resistor R4? Because for the resistor R4, we are provided with the potential difference as well. And if we need to find the resistance, we can simply use the formula R equals to V over I. We are provided with the voltage already. We just need to find the current passing through the resistor R2. So if I trace the currents, this current goes through here, 0.30 amperes. This one also 0.30 amperes. And you see both of them, these two currents combine at this point. At this junction, these two currents combine and collectively they pass through the resistor R4. So what we can say is current passing through that resistor is 0.30 plus 0.30, which is 0.60. And now we do have the value for current passing through R4. Let us insert the values in the formula. The value of voltage equals to 2.4. The value of current equals to 0.60. We hit it on the calculator. 2.4 divided by 0.60. We get 4. So resistance equals to 4. And in 2SF, you can write it as 4.0 ohms. Okay, so you show all the working at this place. Let's take a look at the next part. Gotta speed up. We'll try to solve as many as we can. Determine the EMF of the battery. Determine the EMF of the battery. So if we know the current passing through the resistors, and we also know the resistance of the resistor, then we can find the potential drop across those resistors. So since all of these resistors are same, and the current is also same, like this one current that is going to the battery was 0.60 amperes. that is going back to the battery is 0.60 amperes. So the current flowing out of the battery would also be 0.60 amperes. What does that mean? It means we can find the potential drop over here. We can find the potential drop over here. Okay, these two in parallel would be considered as a single unit because the voltage across both of them would be same. And we can find the voltage drop over here, which is given already. So here also it would be 2.4. And what about the voltage for the two resistors connected in parallel? Well, we can find it would be 0.30 if you use the formula V equals to IR. And I remove this one and all the extra stuff. So V equals to IR. I is 0.30 times the resistance is 4. So 4 times 0.30. What do we get? We get 1.2. What does that mean? We have 1.2 volts over here. We have 1.2 volts over here. Since these two are connected in parallel. So the voltage drop across these two resistors connected in parallel would collectively be 1.2 volts. It remains the same. Even if there were hundreds of resistors connected in parallel, then the voltage across all 100 of them would have been 1.2. So the EMF of the battery has to compensate for this drop, has to compensate for this drop, and has to compensate for this drop. So what we can say is EMF of the battery, which is represented by E, they have represented by E, equals to 2.4 because it has to feed this resistor plus 1.2 because it has to feed these resistors connected in parallel plus 2.4 because the battery has to feed this one as well. So E equals to 2.4 plus 2.4 plus 1.2. What do we get? We get 6 volts. And you can write it in 2SF 6.0 volts. And likewise, there's another way you can answer this question. EMF, because there's no internal resistance in this part, at least negligible internal resistance, what you can say is EMF equals to the total voltage, and that equals to the total current times the total resistance. The total current provided by the battery is 0.60 amperes, 0.60. And what is the total resistance? Well, you have 4 ohms here, 4 ohms here. And these two resistors, which are 4 ohm each, are connected in parallel. The total resistance for which would be 2 ohms. The shortcut is, if you have two resistors connected in parallel which have same resistance, you divide their resistance by the number of resistors. So the total resistance for this pair of resistor would be 2 ohms. So 4 plus 2, 6, plus 4, 10. So 0.60 times 10 would be 6.0 volts. You can answer this way as well. Both the methods are acceptable. Let's take a look at the next one. The battery in B is replaced with another battery of the same EMF, but with an internal resistance that is not negligible. State and explain, if any, state and explain the change, if any, in the total power produced by the battery. So now you have to compensate for the internal resistance as well. So just think about it. If there is the internal resistance as well, then the overall resistance of the circuit would increase. So what do we say? We say the overall resistance of the circuit increases. The overall circuit resistance of the circuit increases. Hence, the overall current would decrease the current that would be drawn from the battery would decrease. So current by the battery decreases, or you can say the current in the battery decreases. That's just the same thing, decreases. And the EMF remains the same. You see, EMF of the battery remains the same. And they have asked you to comment on the power produced by the battery. So power equals to voltage times current. So V remains the same because EMF remains the same. Okay, here we are referring, voltage here is being referred to the EMF. And since the overall resistance increases, then the overall current would decrease. And if I decreases, V remains same, then power would also decrease. Power also decreases. Okay, let's take a look at the next one. The resistors in the circuit are made from nichrome wire of uniform radius. Let me convert it. 240 micrometers mean 240 into 10 power minus 6 meters. The length of the wire need to make each resistor is 0.67 meters. Calculate the resistivity of the nichrome wire. We do have this formula, resistance equals to rho L divided by A. Okay? And we need to find the value of resistivity, so we need to find rho equals to AR divided by L. And we do have to make 4 resistors. So whatever the answer is, we'll multiply by 4. So 4 times area. What is the area for the circular cross section? Pi r square. Pi times r square divided by the length 0.67. And sorry, that was the value 4 because we have 4 resistors times the value of area. This is the value of A to be multiplied by the value of the resistance. Okay, they've asked for each resistor. Sorry, my bad. They have asked for each resistor, the resistivity. So the value of the resistance was 4. We have to find for each resistor. So the value of R, the value of the resistance is 4. The value of the cross-section area would be pi r square and divided by the length of the the length of the wire. And let's hit it on the calculator. Let's see what we get. So 4 times pi times 240 into 10 raised power negative 6 and square of it divided by 0.67. If you want to convert it into the standard form in 2SF, sorry. So 1.1 into 10 raised power minus 6. This is how we answer this one. Let's take a look at the next one, titled as question number 11. So not going to read the statement, we can just have a look at the diagram. And the first part reads, calculate the charge passing through the cell in a time of 7.5 minutes. That needs to be found out. So let us write down the formula of the charge passing through the cell in a time of, so we know that charge equals to I times T. The current is given as 0.80. So 0.80 times how much time? 7.5 minutes to be converted into seconds. Then if you hit it on the calculator, you get 360. Now this one is a very important question and for 3 marks. Calculate the percentage efficiency with which the cell supplies power to wire X. You need to find the efficiency. And here, if you have to find the efficiency, you should not be finding the energy, or you should not be finding the power and then taking the ratio of it, useful output divided by total input times 100. uh, not to be using the energy, you can simply find the power of the battery. So let's see, we need to find, yes, delivered to the wire X. So for this one, let us see what is the power that is supplied by the battery or by the cell, and what is the power that is supplied to the wire X. So let us find the power that is provided by the cell, power of the cell. When you have to find the power that can be provided by the cell, in that case, you have to use the same formula, power equals to V into I. But in this case, what voltage do you take? Well, in this case, you take the voltage equal to EMF of the battery. So for the input, keep it in your mind, if you have to find the input power, the power that the cell should be able to supply or would have been able to supply if there were no voltage drop in the internal resistance would be E times I. And that would be 0.48 times 0.80. And what do we get? We get 0.384 watts. All right, and up next, we need to find the power that would be dissipated across the wire X. And for that one, you're provided with the current passing through the wire X, and you're provided with the resistance of the wire X. So how do you find the power that would be dissipated or that would be provided to the wire X? Well, you use the formula P equals to I square R. So the rule of thumb is, keep it in your mind for all the questions, if you have to find the output power, use the formula I square times R. R being the resistance of the appliance, the external resistance. But if you have to find the input power, use the formula P equals to VI, but the voltage in that case has to be EMF of the battery without any loss. So what is I square R? It is 0.80 square times the resistance is 0.40. And what do we get is we get 0.256 watts. So this is basically your input and this is the output. This is what the battery is able to provide, 0.384 watts. The battery is able to provide 0.384 watts. But because of the internal resistance and the voltage drop over there, the battery is providing only 0.256 watts. Now, what is the efficiency? Output, useful output divided by total input times 100. And if you hit it on the calculator, you get 67% into SF. All right, let's move on to the next part. Find the number density represented by small n of the free electrons. So we do have a formula for the number density that equals to number of electrons per unit volume. And we use this expression to find the drift speed of the electrons. V equals to I over NAE. In the derivation of this formula, we use the same expression. So let us write down the formula. And what do we have for the number of charges? We have 3.2 into 10 to the power 22. That many charges divided by the volume. So let us take a look at the data if we can find the volume of it. So we are not provided with the volume directly, but we are provided with the cross-sectional area and we are provided with the length. And we know this formula also, volume equals to area times length. And matter of fact, this is also used in derivation for the drift speed. So cross-section area is 1.3 into 10 to the power minus 7 and the length is 3. So 1.3 into 10 to the power minus 7 into 3. And if you hit it on the calculator in 2SF, you'll be getting 8.2 into 10 raised power 28. Okay, and coincidentally, the very next question is about the drift speed. So let me write down the formula for drift speed anyway. V equals to I over NAE. You have to memorize it, should be always there in your mind. V equals to I over NAE. I stand for the current passing through the in the circuit. It is 0.8. The current in the conductor is 0.8 divided by the number of charges. Once again, we have small n, the number density. We just calculated the number density over here. It's not given in the data. We just calculated the number density. Small n stand for number density, not the number of electrons. And number density equals to number of electrons per unit volume, and that equals to 8.2 into 10 power 28 times the cross-section area, which is 1.3 to 10 power minus 7, times the charge on electron, which is 1.6 into 10 power minus 19. And if you hit it on the calculator, you get 4.7 into 10 power minus 4 meter per second. So once again, all you have to do is memorize this formula, very important one. Drift speed equals to I over NAE, with n, small n, being the number density, number of charges per unit volume. Okay, then we have the theoretical question. The wire X has the same cross-section area. Okay, this one question we have already solved in the workbook. You can find this question exactly the same. Not exactly, I mean the same question you can find over there. We have explained that over there in the topic of drift speed. So let's move on to the next one. Yeah, this one looks very interesting. All right, for the first part, show that the resistance of the wire is 3.0 ohms. So I'm going to fast forward this one. Resistance equals to rho L divided by A. All you have to do is to insert the values. This is a value of A, this is a value of L, and this is a value of resistivity. So rho L divided by A. And finally write down the answer in 2SF. You should be getting the same answer. Let's take a look at the next one. Okay, so we are provided with the ends of the resistance wire in A are connected to terminals X and Y. Okay, so what do we need to find? We need to calculate current in the circuit, and it has to be for a single mark. And for this one, there is the internal resistance of the battery as well. It's not negligible. So that means the voltage across XY would not be 1.50. So we need to find it first. The potential difference between XY needs to be found out, and then we can use the formula VI equals to V over R, because we do have the value for resistance, but we don't have the value for potential difference between X and Y. Or matter of fact, we do have it. We do have the value of potential difference between X and Y, which is 1.20. So let's write it over here. 1.20 divided by 3. So what we get is 1.20 divided by 3, and I'll just convert it back to the same, 0.4. And in 2SF you can write it as 0.40. Let's take a look at the next part. You need to find the internal resistance. So this is a simpler circuit. It does not get simpler than that. You need to find the internal resistance, and the formula that relates all of them is E equals to V plus I times small r. And we do have pretty much all the values. We do have the current passing through the circuit as well, which is 0.40 amperes. And let us insert the values so we can find the value of R. So thereby, if I rearrange it for R equals to V E minus V divided by I. So what is E? 1.50 minus 1.20 divided by the current being 0.40. So if I subtract these two, I'll be getting 0.30 divided by 0.40, and I get 0.75 ohms. And like I told you, the internal resistance would always be a small number. It's not greater than 2-3 ohms. Maximum could have been 3 ohm, 4 ohm, that's it. But generally it's even less than 1. And what I can see is this question is from the topic of potentiometer. So I'm not going to read the statement. What I can see is the XY, the total length is 2 meters. Okay, it's given in the question. Where is that given? Let me just mark it over here. The length between X and Y is 2 meters and X and P is 1.4 meters. So the total length is, let me mark it over here. The total length is 2 meters, 2.0 meters, and from X to P it is 1.4 meters. Okay, this is given in the question. And the galvanometer is reading 0. So it is the simplest case, the simplest of them all. The only thing is, you have to consider that if the galvanometer is reading 0, then whatever the voltage is across Vx P, whatever the potential difference is between X and P, that would equal to the EMF of the battery. These two would be equal. The voltage across XP would equal to EMF of the battery. The only question is, what is the voltage across XP? That needs to be found out. The voltage across XP. So we can find the voltage across XP if we know the voltage across XY. And we know the potential difference between XY. That was 1.20 volts. So the total voltage between XY was 1.20 volts. For what length? For 2 meters. Because the overall length from X to Y is 2 meters. So for that 2 meters, the voltage was 1.20 volts. And if the length instead of 2 meters is 1.4 meters, then what would have been the voltage? And from there we simply cross multiply that. So 1.4 times 1.20 divided by 2, and in 2SF, as you can see, I'll be getting 0.84. All right, and let's take a look at the next one. Okay, very interesting question, once again theoretical. And this one reads, so I have to go through it, cannot just simply take a look at the drawing. So the figure is modified and the original resistance is replaced with the second one, which has the same length and made up of the same metal. Okay, the second resistance has smaller cross-sectional area. The second wire has smaller cross-sectional area, means it would be having more resistance. Connection P is adjusted on the second wire, so the galvanometer has reading of 0. All right. Stator explain whether length XP for the same wire is shorter than, longer than, or the same as length XP for the original wire when the galvanometer reading is 0, means when it was all balanced, when the potentiometer was balanced. So all you're doing is you're replacing the wire with another wire which has smaller cross-section area. So like, just break it down for 3 marks. The first mark would be if you're able to find the effect of cross-section area, decrease in cross-section area with resistance. So what you say is, if cross section area decreases, I'm just writing the expressions, you can write in description. If cross section area decreases, the resistance would increase. The resistance of the wire would increase. And if the resistance of the wire increases, then the potential difference across the wire XY would also increase, because we know resistance is directly proportional, voltage is directly proportional to the resistance. So if resistance increases, potential difference across wire XY also increases. All right, if I just show you the circuit diagram, if we increase the resistance of this thing, then the potential difference would also increase across XY. And with that thing, if the potential difference increases, then the length of the, to get the same, to get the galvanometer at 0, the length of the second wire has to be decreased. Because if you have more volts on the wire XY and you need to adjust the galvanometer to the same volts, then it has to be slightly to the left side. It has to be pushed slightly to the left side. And once again, you can draw a diagram on that, which I generally show something like this. If I remove everything from here, and let's say previously you're having only how many volts on the wire? You were having 1.2 volts. The voltage across this one was 1.2, and from X to Y you were having 1.2 volts. So let's say you were having, and the battery was being balanced at 0.84. So this is 0.84, and from here all the way over here you were having 1.2. So probably 0.5 somewhere over here, 0.25 somewhere over here. If the overall voltage across XY increases for the second wire, which has higher resistance, thereby it would be having more volts across it. So let's say this time around you have 1.5 over here. Let's say, okay, just an assumption. So you'll be having what, like probably 1.2 over here and 0.84 over here, probably 0.5 over here, then probably 0.2 over here. And you see the battery, the galvanometer was balanced at the mark 0.84 volts. But this time around for the second wire, the 0.84 is slightly on the left side. So this portion, the XY is decreased, XP would be decreased. So you can say the scale is kind of congested this time. You have more values, you have more data across XY, so you get the point 0.84 quickly along XY. Let's fast forward to the next one. The first one being state Kirchhoff first law. Once again, I'm going to skip past this one. A battery is connected to two resistors X and Y as shown in figure. The resistance of X is greater than the resistance of resistor Y. So let's call X has greater resistance and Y has smaller resistance. State and explain which resistor dissipates more power. So keep it in mind, the rule of thumb is, but I'll explain it in details. We have to answer for. Okay, so on to question number 13. If two resistors are connected in parallel, the rule of thumb is, you should memorize this thing as well. The one with the smaller resistance, it would more power would dissipate across that one. So more power dissipated in Y. The rule of thumb is two resistors connected in parallel, the one with the smaller resistance, there would be more power dissipated across that one. But how do we answer that? Obviously, we'll be able to answer this one for 3 marks. You get only 1 mark for the last statement, more power dissipated in Y. But you have to state and explain. 1 mark is for state, 2 marks for explain. So you see, there is equal potential difference between across X, the resistor X, and across the resistor Y. They have same potential difference across them. And the reason being, because they are connected in parallel directly to the battery. But since the resistance of X is greater than resistance of Y, resistance of X is greater than resistance of Y, that means the resistor X would draw less current compared to the resistor Y. They have same voltage, the only difference is the resistance. So the current would more of the current would follow the easier path. So the current through here, IY, would be greater, and the current through the resistor X would be smaller. So this one would be greater, this one would be smaller, because this one was, the resistance was smaller, and over there the resistance was greater. But you have to answer for the power dissipated, and that equals to P equals to V times I. Now, what about the voltage? Not even a comparison, because they have the same voltage across them. So if this thing is same, then we can say power is proportional to current. Or even if we do not write this statement, you can say, since voltage is same, and if the current is more, there would be more power dissipated. So which one is having more current through it? It is the resistor Y. So since current through the resistor Y is greater, hence the power dissipated in the resistor Y would also be greater. So you write all of it. Starting off with potential difference cross X and Y is same, and power dissipated equals V times I. Potential difference is same, and the resistance of X is greater than resistance of Y, hence current of Y would be greater than current of X, hence thereby power of Y would be greater than power of X. Okay, and then you can, I've just written the bullet points, you can write it in description. Let's take a look at the next part. Two resistors, let me check the screen. Yeah, we are fine with it. Two resistors are made of wires that have the same length. Both the wires are made up of same resistivity, same length. And okay, Steiner explained which resistor is made of wire with larger cross-sectional area. You have to compare X and Y, the same one, those which were connected in parallel to the battery. Which one has larger cross-section area? So the one with the larger cross-section area would be having less resistance. How do we know? R equals to rho L over A. So if it has larger cross-sectional area, it would be having less resistance. So let's see which one is having less resistance. Well, it was resistor Y. So since resistor Y has lower resistance, lesser resistance, hence it would have more cross-sectional area. Let's take a look at the next one. I'm going to fast forward this one. Calculate the current in the circuit. So current in the circuit needs to be calculated. If we know the voltage across any of the component, and we know the resistance across any of the component, we can easily find the current. For example, take a look at this component. We know the voltage across it because we have connected a voltmeter around it, across it, and the voltmeter is reading 5.4 volts. So the current equals to the voltage across it, 5.4 divided by the resistance of it. And if you hit it on the calculator, you get 3.0 into 10 to the power minus 3 amperes, or you can write 3 milliamperes, but they are vast in amperes. So this is not only the current through this component, it would be same through all of the circuit, through entire circuit, because all the components are connected in parallel, sorry, in series. All of the components are connected in series. Up next, we have to calculate the resistance RL of the LDR. You need to calculate the resistance of the LDR. So in order to calculate the resistance of the LDR, we can simply use the formula R equals to V over I. Okay, and I'm going to raise off the extra stuff. For example, this one. So do we know the voltage across the LDR? But we do know the current. Okay, we might not know the voltage directly, but we do know the current directly. Current was 3.0 into 10 to the power minus 3 amps. So 3.0 into 10 to the power minus 3. But we do not know the voltage across the LDR directly. But if we recall the concepts of DC circuits, then we can say if 9 volts is provided by the battery, out of those 9 volts, 5.4 volts being dissipated across the first one, and the rest of the share of the voltage would be supplied across RL. So what is the leftover? It is 9 minus 5.4, aka 3.6. So this thing would be getting 3.6 volts. 3.6 volts across the LDR. So 3.6 divided by this 6 divided by 10 raised power minus 3, we get 1200. So that's the end of it. And in the description you can find the link to my Patreon page, and over there you can find the solved, unsolved worksheet, past papers, topical past papers, the workbooks, solved and unsolved, all of them. All you have to do is just to click on the link. You can see it in the description, and you'll be directed to the Patreon page. You can just buy the subscription of any of the tier, and there you go. You'll be having the access to the entire stuff, all the solved and unsolved materials you can find over there.